Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And here we're going to illustrate part 4 in a series that I'm calling One-Way Fixed Effects ANOVAs. In part 4 we looked at the sum of squares deviations. Now in part 3 we use more of a matrix based and quadratic form based to derive the sum of squares. Here we're going to use more of a scalar form, and that's with in quotes because R tends to do things in vectors anyway, so it's going to be a little bit hard to illustrate that, but that's the goal of this video. Now I'm also under the assumption that you have watched parts 1, 2, and 3, which I'm going to highlight and load and not really talk about. The example that we're doing is from a book by Montgomery called Design and Analysis of Experiments. It's the 3rd edition, and we're looking at example 3.1. They call it the tensile strength experiment, where they look at different fabrics with different percents of cotton in it. So a 15% blend, a 20% blend, up to a 35% blend. And tensile strength is that they pull it apart, and how much pressure it takes to tear is what's called tensile strength. And so that's the experiment we're doing. So I'm going to load parts 1, 2, and 3 and then go to part 4 and illustrate the derivations. So first we'll look at the sum of squares total, which is it's the y minus the mean squared summed over all y. And that's what this represents. And as I do this, so this is a vector of the y's and this is a vector of the mean, and we're subtracting the mean, and then this vector product creates that sum. And then I thought, that's really not scalar form, right? It's still a vector. And notice that they don't put sum of squares total in the design, but that's okay. But then I thought, well, let's keep it more scalar-like. So we have a vector of y, and then we subtract the mean, then we square each component, and then we sum each component. And that's what this represents. And we get the same thing. Now if we look at the summary of our one-way fixed effects model, and then we created an ANOVA model, and that's what is stored in this variable. Notice it has degrees of sum of squares treatment, sum of squares residual. The addition of these two is actually equal to 636.96. And to prove it, what I do is I take this table, I grab this column, and then I sum it. So I take the summary, I want the first object, which is this table, I want column sum of squares, sum square, and I'm going to sum it. And it is 636.96, same as what we got before. Now the sum of squares residual is the data minus the fitted value squared and then summed over all y. And that's what we get here, 161.2. Notice it's the same. And then this is more, I'm going to call it scalar-like. We have our y data minus the fitted value. We're going to square each component and then sum it. That's 161.2. And if you look at the summary, we get 161.2. Now, sum of squares treatment is the fitted value minus the grand mean squared summed over all possible values, or summed over each treatment mean, really. And so that's what this is, and we get 475.76, which rounds to 475.8. More scalar-like version, we take the fitted values, subtract off the grand mean, square each component, and then sum. And if we look at the summary, that's indeed what we get. And then the rest of the table is actually, sum of squares divided by degrees of freedom, sum of squares divided by degrees of freedom, and everything just falls out. And you can watch part 3 for more detail on that. So next is we're going to illustrate part 5 in R. So that's it for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.